Jenard. She's my good friend, and also she's a co-creator and co-chair of the REYES program. She's in the call right now, but she might be multitasking. She's also at work. So.
Oh, nice to meet you. Hello.
Yeah. Giovanna is one of those crazy people that don't have to do science for work, but they love to be a science advocate. So she puts a tremendous amount of hours in running this program. So I couldn't really do this without her. So
that's awesome.
Yeah, for sure. I see another question about the Python class. It was recorded, so it should be on the YouTube page. I will edit the YouTube page a little bit in the next few days to make the new recordings more easily accessible. But if you go to the tab that says live, there you will see lots of recordings, including the Python one. They might not be properly labeled just yet, but again, that's because I'm juggling multiple things at once. Okay, I think we can go ahead and introduce today's speaker. So let me pull out my handy dandy notes. So our next speaker is Phiala Shanahan. It's a real pleasure and to introduce her. She got a PhD from the University of Adelaide in 2011. After that, she joined. Oh, you're shaking your head. Did I get the date wrong?
2015.
Oh, 2015. Why did I have 2011? That doesn't even make sense. I met you after I was here. So yeah, 2015. And also I got my PhD in 2013, and I'm obviously older than you. So I don't know. I lost my mind there. 2015. Thanks for the correction, Phiala. After that, she joined a little known university, MIT, as a postdoc. In less than 2 years, she became faculty at the College of William and Mary. And less than 2 years after that, she went back to MIT to become faculty there, where she is now an associate professor. She has a long list of accolades and awards. She's a recipient of the NSF Career Award, also the DOE Early Career Award. She was named as one of the Simons Foundation Emmy Noether Fellow. She's been listed as a Forbes magazine 30 under 30 in science in 2017. She's gotten several research awards, including the Ken Wilson Award for her contributions to lattice field theory, which reads for excellence in the study of hadrons and nuclei in lattice QCD, and for the pioneering application of machine learning and artificial intelligence techniques to lattice field theory. She got the Maria Jeppard Mayer Award of APS in 2021. This is all to say that Phiala is a force to be reckoned with. She's really a rock star in our field. She's leading different collaborative efforts. She's an excellent speaker, but she's also puts a great deal of time on developing ways to help young people be promoted in the field, including a colloquium series that she hosts virtually. And I think this started during the pandemic, so around the same time as REYES. So, yeah, it's just a real pleasure. I was really delighted when she agreed to join. And she's so flexible that she's actually hosting a workshop out in Italy, and she's joining us from there. So we really appreciate for you to take time out of your busy schedule to join us. So with that, Phiala, the floor is yours. Speak for however long you want, and then when you're done, I'll read the questions from students. For those of you that are joining us, please put the questions in the Q&A box, and I'll get to them afterwards. So please take it away, Phiala.
Thank you very much. Yeah, it's a real pleasure to be part of this program. Thanks for the invitation. And to tell you just a little bit about our modern understanding of the structure of all of the matter in the universe. So you should see some themes coming back from the other lectures I know you've had in this series this year. But so let's start at the start. Matter that makes up you, me, the Earth is of course composed of atoms. And those atoms have densely packed nuclear cores made of protons and neutrons, orbited by a cloud of electrons. And our modern understanding is that the structure of matter goes deeper, exactly one layer deeper, and that the protons and neutrons inside an atomic nucleus themselves have substructure. They're made of matter particles called quarks, which are held bound or glued tightly together by the strong nuclear force, which is manifesting as force-carrying particles called gluons, so very apt name. And to the best of our current understanding, as I think you might have heard in the last lecture, the quarks and the gluons are it. They're fundamental particles. They can't be divided any further. So the quarks and the gluons and their interactions are encoded in what's known as the standard model of elementary particles. The framework was put together in the 1970s, and it has just 17 fundamental particles. You can see them here on the slide, and describes 3 of the 4 fundamental forces. So we see here the quarks. They're the matter particles who we just met before, who come in different types or flavors. We have particles like the electron and its neutrino, and their heavier cousins. We have the force carriers for 3 of the 4 fundamental forces. So we have the gluon, who we just met before, for the strong nuclear force, the photon for the electromagnetic force, and the W and Z bosons for the weak force, and of course the Higgs boson, which was the last piece of this puzzle to be found experimentally in 2012 at the Large Hadron Collider. That's 4 decades after it was predicted from the theory. And this was just the most recent. And so again, to draw back to what I think you might have heard in the last lecture, actually many of the standard model particles here were predicted from the structure and from the symmetries of the theory before they were ever seen experimentally. So if we go back to just the most recent few, there were the W and Z bosons in 1983, the top quark in 95, the tau neutrino in 2000, and then the Higgs in 2012 was the last piece of the puzzle. So this is the particle content. And the standard model describes, as I said, 3 of the 4 fundamental forces. So electromagnetism, that's the forces between charged particles. We have the strong force, that's the strong nuclear force, which binds the quarks and gluons together into protons and neutrons, and binds those protons and neutrons together into nuclei. We have the weak nuclear force, which is responsible for processes like radioactive beta decay that you might have heard of, but it doesn't describe gravity, which is described by the separate theory of general relativity. So this is the framework. The equations that describe the theory are here on this mug. They're beautifully symmetric, they're elegant, and as I said, this theory, which was developed in the 1970s, has successfully explained and predicted an incredibly wide variety of experiments and phenomena. So what I'm trying to say really is that the standard model has become a well-tested physics theory, arguably the best theory of the matter in our universe that we've ever had. And so my goal in this lecture is to give you a little bit of a sense for how successful the standard model is, and then a feeling for what some of the questions are that we're addressing now, sort of at the cutting edge in terms of standard model physics. So to give you just one example of the extraordinary success of this theory, what we're looking at on this slide is the magnetic moment of the electron. What that means, that's how much torque an electron feels when you put it into a magnetic field. So that's described by this number here. And this number is the most accurately verified prediction in the history of physics. So you can see a comparison between the number from theory and experiment. We have here agreement to 12 significant figures. And just for a sense of quite how heroic the effort was to achieve this took 30 years of effort to do this theory calculation here. And in the end, after that, we see this beautiful agreement between theory and experiment. Now, to the best of our understanding, the standard model also describes many more complicated aspects of the structure of the matter in our universe at all distance and all energy scales. So from the structure of the proton at the most fundamental level, and that's what this cartoon is showing here. This is showing a proton with this complicated bubbling mess of quarks and antiquarks and gluons holding them all together. What we've learned from the standard model about the structure of the proton is that at this deepest and most fundamental level, these building blocks, these particle building blocks of the universe, don't behave at all like Lego blocks. What we see is that pairs of quarks and antiquarks can appear from empty space. We call this the quantum vacuum, and they can annihilate again, giving us this bubbling, dynamical quantum vacuum that defines the structure of all of the matter in our universe. So if we look at a proton using higher and higher energy scale probes, we see more and more of this complicated bubbling dynamical structure coming out, and we can understand this from the standard model. In principle, our understanding of the standard model goes all the way from the structure of a single proton to the structure of the elements which are built from protons or neutrons. So you'll recognize here the periodic table, all the way to nuclear reactions at a cosmic scale, like the nuclear reactions that power the burning of the sun, or the nuclear reactions that happen in reactors for energy generation, for medicine, all the way to the dynamics inside neutron stars. So neutron stars are the most dense known objects in the universe other than black holes. And to the best of our understanding, this beautiful, elegant standard model theory describes all of this. However, I believe you've also heard earlier in this year's lectures that despite its successes, we also know that the standard model does not describe everything we observe about the universe. And so we make massive efforts as a physics community to understand and to constrain the physics beyond what's described by this best physics theory we've ever had. And again, we can connect to another theme in the program so far. So for example, the standard model cannot explain dark energy, which is the name we give to whatever it is that's driving the accelerating expansion of the universe. And in addition to that, we actually know that most of the matter in the universe is not described by the standard model at all. It's in fact the mysterious matter that we call dark matter. And we'll talk a bit more about dark matter later, but essentially it's non-standard model matter that we know is there because we see it interact gravitationally, even though we don't know a lot about exactly what it is or its properties. And so we're left with our beautiful best physics theory ever describing just this little slice here of the universe's energy density pie chart. And that's not all. Of course, gravity doesn't fit into the standard model. And there are also other hints that our theory is not quite complete. The fundamental particles called neutrinos, they're massless in the basic standard model, but they have masses in nature. There's an asymmetry between the amount of matter and antimatter that we see in the universe that we can't explain. So all of the stars, the galaxies seem to be made of matter. But if we start with the Big Bang and allow only standard model interactions, we can't understand why there's such a difference between the amount of matter and antimatter left over at the end. There's lots of questions we can ask about the naturalness of various parameters in our theory, why they take specific values. And so, of course, one of our primary missions in physics is to understand in what ways our best current theory of nature falls short of describing what we observe about our universe. So just one of the many ways we look for what we call new physics, so physics beyond this theory, is at what's called the intensity frontier. Now that term is used to describe experiments that have the sensitivity to probe really, really rare standard model interactions. So if we're looking for really, really rare events, we want to build really, really big detectors to increase our statistics and our probability of ever actually seeing the event happen. And what those big detectors, those experiments are built with is with the matter that we can assemble en masse here on Earth, right? So they're built of nuclei, protons and neutrons. And so this brings the standard model back again, that to constrain the physics, the new physics that we're searching for, we have to actually also understand quantitatively, numerically, the physics of the nuclei that we're using in our detectors to look for the new physics, right? So one example of these types of experiments is dark matter direct detection experiments here on Earth, where we're looking for dark matter to directly hit and interact with nuclei in our detector. Another example is what you see in the cartoon on this slide. This is called the Deep Underground Neutrino Experiment, which is currently under construction in the USA to learn more about the properties of neutrinos. And so these diverse experiments, from those looking for dark matter to those studying neutrinos, have in common that we really need to understand the standard model physics of the nuclei in the detectors in order to constrain the new physics. Okay, so this is really putting this in context here, that we want to study this theory, the standard model theory. And that's both for its own sake, because we want to explore the structure of matter in the universe. Can we really go from this fundamental theory and understand the proton's internal dynamics? Can we really go from our fundamental theory and understand nuclear reactions? But also, it's critical to do this to be able to constrain the backgrounds and the benchmarks for many searches for physics that we know is there beyond the standard model. Okay, so after a little bit more introduction, I'll give you some examples, some older and some from really new research in both of these categories. And then at the end, I'll talk a little bit more about how modern advances in algorithms and computing are really driving this way of studying the standard model further. But first, a little bit more introduction. So if we want to talk about doing calculations from this theory, from the standard model theory, one part of that theory that's really important is the part that describes the strong interactions. That part of the standard model is called quantum chromodynamics, or QCD. And remember, the strong interactions are the force that's responsible for binding the quarks and gluons into protons and neutrons, and for binding the protons and neutrons into nuclei. And so if we want to study things like the structure of those protons, neutrons, and nuclei, we really have to understand the strong interactions. So this is a critical piece. But this part of the standard model is really, really difficult to study. And that's because it's what's called non-perturbative at low energy scales. And I'll explain what that means. Looking here at this figure, we have on the vertical axis the coupling of the theory, that's the strength of the interactions in this theory. And on the horizontal axis, we have the energy scale that we're using. Now, if we go to large energy scales, so to the right of this figure, this interaction strength, or this coupling, is a very small number. That's very convenient, because what that means is one interaction is much more important than having two interactions, because if you square a small number, it gets even smaller, right? And then 3 interactions is even smaller again. And so if you're studying the theory in this energy regime, you can go to some number of interactions and know that all of the extra terms that you're ignoring are even smaller and not relevant to the precision you're working at. But if we're interested in low energy, so moving to the left of this figure and even further to the left than this figure even shows, this coupling gets very large. And the problem with that is that we can't do this expansion anymore. 2 interactions is just as important as 1, 3 is just as important again. And so there's no way of making a series or stopping in the calculation. Now, why are we interested in low energies here? Well, that's what's relevant to, say, the structure of a nucleus at rest in a detector waiting for dark matter to hit. So we really have to be able to do calculations over here where it's really difficult to do them. Now, what we're left with, the only way we know to study the strong interactions at low energy scales in a way that's systematically improvable, and by that I mean that you can do a calculation and you know what series of calculations you have to do to converge to the correct answer, is through an approach known as lattice field theory, or lattice QCD, if we're studying the strong interactions, QCD. And what calculations in this framework look like is very, very high dimensional integrals, right? So essentially, I heard there was some talk about fields in the last lecture. So we can take fields describing the quarks and gluons, these particles, and put them onto a grid or lattice. That's what gives this technique its name, lattice QCD, in such a way that you can solve the equations numerically. And so what you're really left with is very, very high dimensional integrals in something like 10 to the power of 12 dimensions. That's a million or a trillion dimensions of these integrals. That's at the scale of state-of-the-art calculations that are being done today. And doing that is just a massive computational challenge. So the challenge is so large that even with the most powerful supercomputers in the world and investing significant resources on those supercomputers, so in the United States, something like 10% of public supercomputing goes towards just these sorts of calculations every year. Even with that, we're still computationally limited. So that means there's problems that we know how to solve, that we need to solve, and we just can't with the amount of computing that currently exists in the world. And I'll come back to this as a motivation for new algorithms later in the talk. But for now, just to give you a sense of scale, I'm going to show you some calculations a little later, which would take something like 10 to 50,000 years on the laptop I'm using to call into this talk. And another sense of scale is, so this is not the largest, but one of the largest supercomputers that we're running calculations on at the moment. It's called Aurora. And if every person on Earth did 5 calculations every second, it would take everyone on Earth together about a year to do what this computer can do in 1 second. So we're talking really, really massive scales of computing. But as we'll see, these calculations, in fact, can be done. And as a result, we have this beautiful complementarity at this point in time between theory, where we start with just these 17 particles in the standard model and the equations that describe their interactions, and we compute what we expect to see in the universe, and experiment. This is a picture of particle collisions at the Large Hadron Collider. And so there's this beautiful complementarity between theory and experiment. Okay, so let's come to some examples of how we can use this approach of doing these massive numerical calculations to study the standard model and learn something about the complex structure of protons and neutrons and nuclei in nature. Now let's start with the first example. So we know, because we can measure it experimentally, the neutron is ever so slightly heavier than the proton. And this is really absolutely essential for life as we know it. If the proton was heavier than the neutron, then it wouldn't be stable. That means that protons, and remember, protons are the nuclei of hydrogen atoms, they could decay. And that would mean that the sun couldn't have survived for more than a century after its formation. Solid bodies would collapse into neutron stars or black holes. No atoms would ever have formed. We wouldn't be here to know anything about it. So there's this very small but very critical mass difference between protons and neutrons. And we can measure that mass difference from experiment. That's this orange band here. But with theory calculations, we can actually understand this mass difference. And so this is really from the last 10 years or so that we can see where that very small but very important mass difference comes from our fundamental theory. And in fact, we can see that it's a delicate balance of the strong nuclear force pushing that mass difference in one direction and the electromagnetic force pushing it in another direction, which gives us a delicate cancellation to give us exactly the value that we measure experimentally. So this is a first example of the complementarity between theory and experiment in understanding what we observe about the matter in our universe. Now let's come to something a little bit more recent. So I only have time to give you a little bit of a taste here, but these sorts of direct, we call them first principles calculations of the standard model, can also reveal aspects of proton structure that we can't measure so easily experimentally. So here's an example that is a little bit intuitive. This is a cartoon of the pressure distribution inside the proton. Now, the proton is stable and the quarks inside the proton are confined, they can't escape. So what that means is if there's some sort of pressure pushing those quarks out of the proton, there also has to be a pressure pulling them in, right? And so what we're seeing here on the plot is here's the center of the proton. And we're moving out along the horizontal axis from the center of the proton along a radial direction. On the vertical axis is that radial distance squared times the pressure. And I'm showing this combination because this is the combination that has to integrate to 0 for the proton to be stable. So if there's a peak here, that's a repulsive pressure pushing out, there also has to be a trough. That's a confining pressure pushing in to balance it. Otherwise, the proton wouldn't be stable. So we can draw this cartoon. If it goes up, it has to come down without any measurements or any calculations at all. But as soon as we have the cartoon, we can start to ask questions about it. We can say, well, what's the peak pressure in the proton? Should it be like a black tire? Should it be more like the bottom of the ocean? That's about 1,000 times more than a black tire. Or what about like the highest pressure we've ever created in the lab? That's something like 1,000,000 times a black tire. Or more like the interior of a neutron star. So that's one of the densest known objects in the universe other than a black hole. And the pressure inside a neutron star is something like 1,000,000,000,000,000,000 million times the pressure inside a black tire. Well, what about the proton? We can ask, how far out does the pressure in the proton go? Is this the same as what we usually think of as the size of the proton's radius? What we usually mean when we say the size of the proton is the radius of the proton as seen by an electromagnetic probe. And we can ask, is that the same or different from the radius of its pressure distribution? We can say, well, we know protons are made of quarks and gluons. They're the fundamental particles. How do these different fundamental particles come together to generate this pressure distribution? Do their contributions look the same or do they look different? And so this is an example of something that just in the last few years, we've been able to answer by combining theory with experiment. So what you see here in this figure, what you see here in this figure is just like the cartoon we saw before, but now it's real data. So now what you're seeing is in green, the quark contribution to the proton's pressure distribution. Now that was measured experimentally just a few years ago for the very first time. In pink, you see the gluon contribution to the pressure distribution, which at the time had not been measured experimentally, but we were able to calculate from theory for the very first time. And in blue, you see the combination. And so what we find by combining theory with experiment is that actually the pressure inside a proton is greater than the interior of a neutron star, that the gluon contributions here are significantly pushing out the size of the proton by this measurement of the pressure distribution. And so it's really an example, it's a very recent example where theory and experiment together have given us a complete picture of this sort of fundamental aspect of proton structure for the very first time. Okay, so let's turn now from the very, very small, so the dynamics inside a single proton, to the cosmic scale. And as I said before, our understanding is that the same model of elementary particles that describes the proton structure describes the primordial nuclear reactions through which the universe evolved. So immediately after the Big Bang, the world, the universe, was a hot, dense particle soup. And as the universe expanded and it cooled, matter and galaxies formed. So 1 second after the Big Bang, the universe was filled with neutrons, protons, electrons, positrons, photons, and neutrinos, and that's it. And from there, the various elements were created by a chain reaction called Big Bang nucleosynthesis. And so this chain reaction happened in the roughly 10 seconds to 20 minutes after the Big Bang. And that's what you see here in this figure is the start of the pathway by which heavier and heavier elements formed. So this very start of the chain reaction here, we see a neutron and a proton coming together to form a deuteron, that's a nucleus with a neutron and proton inside. And then we see those combining to form heavier and heavier elements. Now, this very first part, where the proton and the neutron come together to form a deuteron, is not only the very first nuclear reaction that occurred in the universe, but it's also the first nuclear reaction that we were able to calculate a few years ago from the Standard Model directly. And so what we're seeing is that we can indeed do that calculation. This is about the most complicated plot that I'm going to show in this talk. And that's because I want to give you not just the big picture, but also a little bit of a feel for how these calculations are really done at the most basic level. This process here was one of the first processes where we could really see that the reactions between a photon and a nucleus are different from the couplings of the photon to the individual protons and neutrons. So what that means is there's really some two-body, some nuclear component. And that's what's being shown here on this figure, the two-body component of this reaction. So the piece that's not from the photon coupling to the neutron and proton individually, but really a photonuclear reaction. Now the yellow star is the relevant value in nature. And on the horizontal axis is the mass of a pion. Now that's a particle formed by a combination of quarks. Now this pion, it has a value in nature, and that value is all the way over here. So what I'm showing you here is fictitious universes where the quarks are heavier than they are in our universe. And because of the computational cost, these calculations are so computationally expensive that we can't do the calculation in the real universe. But what we can do is do the calculation in a universe where the quarks, the fundamental particles, are a bit heavier than they are in nature. And if we do the calculation at multiple values, then we can draw this band and extrapolate down and see that our extrapolation gives this band here, which is completely consistent with the value in nature, right? This is sort of how the sausage is made here. In this case, we have this experimental result to compare against. We can see that this method of doing the calculation and then drawing the line, extrapolating down agrees with experiment. But now that we know we can do this, we can do calculations for many other applications where we don't have experiments, or where experiments are really difficult or have large uncertainties. And in those cases, we again see that combining theory with experiment gives us really new insights into the universe. So one more example of an important nuclear reaction that just in the last few years we've been able to calculate from fundamental theory is one involved in the chain reaction that powers the sun. So the sun emits light through the conversion of hydrogen to helium in a nuclear chain reaction that you see here on this slide. So here we get combined again, this is the chain reaction. And you see at this stage, we have photons being emitted in the chain reaction. And those photons, that's what works its way out to become the sunlight that we see. Now, the very first step of this chain reaction is proton-proton fusion. Two protons here fused together. And this again, we've recently calculated for the very first time from the Standard Model directly. So this is sort of the cutting edge of developments here. And so the way you should think about this is that we can't yet do calculations of any nuclear reaction you can think of. That's just too hard computationally. But we are at this very exciting moment. We're at the beginning. We're entering an era of being able to understand not just the proton structure, but nuclear physics from fundamental particles, from the Standard Model and these beautiful, elegant equations. That's our best physics theory we've ever had. And so it's a really exciting time in this area for the next decade or two. Okay, so let me come to another example. I said that studying the Standard Model is both really exciting for its own sake, like this. Can we really understand nuclear reactions from fundamental physics? But it's also important for our searches for physics beyond what's described by the Standard Model, as I said before. So let's just take one example. By about 1980, it was pretty widely recognized that we have a significant problem in our understanding of the universe, that what we observe looking out at the stars, the planets, the galaxies, doesn't match what we understand. And so this picture shows what's called the Coma cluster. That's a large cluster of galaxies that we can see from Earth. And for this particular cluster, it had been noted as far back as the 1930s that something doesn't quite add up, that the gravitational attraction that would be needed to hold this cluster of galaxies together is more than can be possibly generated by the luminous matter, by the stars that are emitting light. So it's like there's something else acting gravitationally to hold the cluster together. Something that's acting like matter does gravitationally, but it's not emitting light, so it's dark, right? Dark matter. And so we see similar evidence for dark matter in many, many other ways. And I'll give you just a couple of examples. For example, in the rotation curves of galaxies. So here we have a nice galaxy here. And in this figure, on the horizontal axis, we're moving out from the center of the galaxy. And on this axis, we're saying how fast everything's moving. So the red curve shows what we expect from the visible matter, the matter emitting light, and from standard Newtonian gravity. And the white curve shows what's actually measured. And you can measure that using starlight or using the Doppler shift in the 21 centimeter hydrogen line. But what you see is that in the data is that everything seems to be moving too fast. And what that means is that, so here, the measured is faster than the calculated. And what that means is that unless there is extra matter acting gravitationally, this galaxy shouldn't be held together at all. It should be flinging apart into space as it rotates. So again, it's like there's something else acting like matter that we can't see. And here's just one last example. So this is the famous bullet cluster. This was discovered in 1998, I think. And this is an example where we're really able to see clusters of galaxies collide. So in blue, in false color, is the location of the matter that we can infer is there through its gravitational interactions. The way we do that is by looking for light, how light from other galaxies is bent around the matter through what we call gravitational lensing. And in pink is highlighted the visible matter that we can see through light or through X-rays. Now there's less than 1 in a trillion chance that the separation between the blue and the pink, between the matter that we know is there or we can deduce is there and the matter that we can see, there's less than a 1 in a trillion chance that that's a statistical fluke. And we can also understand this separation within the framework of dark matter. So if we start with galaxies which have matter and dark matter sort of equally distributed and they collide, the dark matter just sails right on through while the visible matter collides and gets stuck in the center here. So we can even see that. Here we have blobs where the matter and dark matter is sort of equally distributed. And as the cluster of galaxies collide, the normal matter collides and gets stuck in the center and the dark matter just keeps on going. And you get the separation, which is exactly what we see. And it's not just the bullet cluster. Since then, there have been many other examples where we see similar separations. So we deduce from all of these sources and more that there is something acting gravitationally that we can't see. It's really very mysterious. We've never seen dark matter directly in a detector, but we've deduced its existence from overwhelming evidence. And so we know that about 5 times as much of the universe's energy density pi is this mysterious dark matter as the fraction that's described by the standard model that we know and love and can calculate with. So let's think about what is dark matter and how does it interact? So we know that it doesn't interact through electromagnetism. It's dark, right? We know that it doesn't interact through the strong force because cosmic rays, they're made of protons, they don't interact with it. It certainly does interact through gravity. That's how we know it's there. And if it only interacts gravitationally, it will be very hard to see it, detect it directly or make it in a particle accelerator. But it's possible that maybe, just maybe, dark matter might interact with the standard model through the weak interactions. And then we have a chance of detecting it with experiments here on Earth. Now that's an example. It's certainly not the only possibility for dark matter, but it's one that I want to focus on for a moment. And although we don't know what dark matter is, we know something about how it interacts. That's what we just said. And we also know what it's not. So it's certainly not stars and planets because it's dark. It's not dark clouds of normal matter because it doesn't absorb radiation. It's not antimatter. Otherwise, we'd see the unique gamma ray signals that are produced when matter annihilates with antimatter. It's not galactic mass black holes on the basis of how many gravitational lenses we see. Although in some cases, there's some corners of those parameter spaces that aren't entirely ruled out. This is fairly clear. So we know what it's not. We don't know what it is, but we have a lot of theories for what it could possibly be. From theories with extra dimensions or supersymmetry to new particles like dark photons or axions or sterile neutrinos or extra copies of Higgs particles, right? And so we have lots and lots of ideas, not a lot of constraints. And then the idea is that we want to do experiments to rule out parts of this parameter space and support others so that we can whittle down these possibilities for what dark matter could be. And all of these theories that we have, they predict dark matter, which would have different properties. So here I have just a couple of examples in this chart where we have the mass of the dark matter particle on the horizontal axis and how strongly that dark matter would interact with the proton on the vertical axis. Now, this is certainly not a complete list. This is just to give you a feel for it, that different theories would give different dark matter candidates that live in different pieces of this space. So if we can put constraints on this space, then we can maybe rule out some theories and not rule out others. For example, that looks like this. Now, this plot looks quite complicated, but it is actually exactly the same figure that we just saw before. On the horizontal axis, we have the particle mass. And on the vertical axis, we have how strongly dark matter interacts with a proton or neutron. The lines on the figure show different experiments. And the way to read this is that each line is ruling out all of the space above the line. So because of this line here, we can't have a particle with this mass and this interaction, otherwise we would have seen it, right? So each of these experiments has not seen dark matter, and that lets them put a constraint on this space. Okay, now a very important thing here is that these experiments here, as we discussed right at the start, typically use very large nuclei in the detectors. All of these ones with X's in the name, they use xenon. That's a very big nucleus with 130 or 140 protons and neutrons. But what this figure is showing here is a constraint on the strength of interaction of dark matter with a single proton. So there's been a translation between not seeing dark matter hit xenon and what that means for how strongly dark matter interacts with a proton. And this is where we need to understand the standard model. Essentially, all of these constraints assume that dark matter interacts with a single proton or neutron inside that big nucleus at a time. But again, just in the last few years, we were able to actually calculate this and see that interactions where dark matter would interact with multiple protons and neutrons in a nucleus at a time are actually much more important than we might have thought. And what that means is that to really interpret what it means for our theories of dark matter from not seeing dark matter hit some large nucleus, we need better theory understanding, which means better calculations from the standard model. So, as I said, it's a really exciting time where we're just beginning to be able to do some of these complicated calculations of dark matter hitting a nucleus. But many problems are still just computationally much too expensive to do. And so just for a sort of sense of this, if we want to do calculations with larger and larger nuclear systems, the computational cost explodes. And it explodes like an exponential and a factorial. That's just a massive explosion in cost that we can only do calculations for atomic number, that's the number of protons and neutrons, less than about 5. And the chances of getting larger anytime soon are really, really limited by the available computing. But we'd really like to be able to push this computational barrier, right? We'd like to be able to study dark matter interactions with larger nuclei like the ones used in experiments. Neutrinos, remember they're the mysterious particles in the standard model where we don't fully understand their masses. We'd love to be able to give input to those experiments looking to understand neutrinos better. There's a fascinating process called double beta decay which could tell us whether the neutrino is its own antiparticle or not. That's something we don't actually know the answer to. And theory calculations would be really important, again, towards deciding which experiments will be the best ones to do to answer that fundamental question. And so even though we can do so much now, it's really would be great to be able to push further. And that brings me to the last segment of the talk, and that's how can new algorithms based on, in particular, things like machine learning and artificial intelligence, open up new possibilities in these calculations from the standard model. And I want to give you just a little taste here. So when we're talking about using artificial intelligence for theoretical physics calculations, one thing is really, really critical, and that is we're doing calculations of a well-defined, precisely defined mathematical theory. And so that means we have to preserve exactness in all of our algorithms. We have to do provably exact artificial intelligence. There's no room for a black box or for some uncertainties that we don't know how to control, right? If 2 + 2 is 4, you better get 4 no matter how you do that calculation, whether or not machine learning is involved. And so what that means is that we need to set up algorithms for doing calculations where no matter how bad the artificial intelligence is, the AI is, you guarantee that your results will be correct. And so you create a situation where if you have a well-trained or a well-optimized artificial intelligence, you'll get the correct results really fast. But if you have a really badly trained artificial intelligence, you'll still get the correct results, but maybe it will be really computationally slow and wouldn't have been worth doing in the first place, right? So we have to use artificial intelligence or machine learning in a different way from many of the applications in industry. We have to really guarantee mathematical rigor. And I'll give you just one hint of one of many ways that we're working to do this for these calculations from the standard model. And I think this one's sort of fairly easy to get a sense for, is that the first step of any one of these lattice QCD calculations, these lattice field theory calculations, these massive computations that I talked about before, the first step of any one of those is essentially a sampling problem. We have to sample field configurations, so that's background configurations of the quarks and gluon fields, according to a known probability distribution, which is just given by the theory, by the equations that describe the standard model. And what you can picture that as is, if this is a sample here of field configurations, these ones here are very likely. They happen very frequently. I want a lot of them. This is just random noise. That's very unlikely. I don't want a lot of those. And so I want to generate these samples so that I get a lot that look like this with these sort of correlations on a canonical scale, and not a lot that look like this random noise here. So there's an immediate parallel between this problem and a problem that's received a lot of attention in the machine learning community. If I want to generate samples that look like this and not this, it feels a lot like the problem of generating fake pictures of people's faces that look like this and not random noise. And of course, artificial intelligence is really extraordinary at creating fake photos now. You can design machine learning algorithms that spit out these and never give you noise. And so I should be able to do the same thing, to spit out these and not give me noise, right? So there's an immediate parallel. There's also a very clear and immediate difference. So in an image set, every image is a good face or not on its own, right? You can look at it and you can say, oh yeah, that's a believable face, or oh, that looks a bit funny. Whereas the field configurations, you can't do that. It's really only the set of all of them that needs to follow some precise probability distribution that has any meaning at all. But there's also other differences. This picture is described by something like 3,000 numbers, and in a benchmark image set for machine learning, you might have 60,000 pictures, right? For our field configurations, each image or field configuration is described by this many numbers. But we might only have 1,000 samples or so. So this ratio here is very different to this ratio here. And what this means, this inversion of this hierarchy, is that we're not going to be able to do standard types of machine learning where you need a lot of training data to train your algorithm. there's other differences too. So local structures are very important in the image. The eyes and the nose, their own local structures. The long distance structures are really what encode the physics. So things like convolutional neural networks that you might have heard of that have really been developed with images in mind and these local structures in mind won't really work for these applications. There's lots of differences in the symmetries. Images don't have a lot of symmetry, but field configurations can have really complex physics symmetries. So it becomes clear very quickly that although it feels the same, there's very significant differences. And if you want to use artificial intelligence or machine learning tools for these sorts of theory calculations, you really have to go back to the drawing board and from the ground up, develop these approaches for the physics problems with all of the physics built in. So this is just an advertisement here for, we have a center called IFI, the Center for Artificial Intelligence and Fundamental Interactions. And we actually have a lot of online resources also from our summer schools and workshops that sort of have lectures about machine learning and how to put physics inside it. Okay, so however, if you go back to the drawing board and you develop machine learning with all the physics built in, it can be very, very effective. So here I'm showing you just sort of a hint of the success that these types of algorithms are having in this area. So on this figure here, this is a measure of the cost of generating these field samples. And remember, generating these field samples is the very first step of any calculation, whether you want to calculate something about the proton or something about dark matter scattering from a nucleus. The first step is always this sampling step. And on the vertical axis is a parameter of the theory. In fact, going from left to right, we're making the spacing of the grid, the spacing of the ladder smaller. And of course, that's a limit we have to take to return to the continuum world that we know. So these colors here, the orange and the gray, those are conventional sampling algorithms. And you can see moving from left to right, these costs get much, much larger. They explode. Whereas this is a machine learning accelerated sampling algorithm. And you can see the cost is much, much less. Over here, it's a few orders of magnitude, say a factor of 1,000 cheaper than using conventional approaches. So this is very, very exciting. It's also very, very new. So it's not clear yet whether this will have the impact we're hoping for in nuclear and particle physics. And again, this is something where the next 5 or 10 years will be very exciting to see if these sorts of new tools can open up new computational frontiers for us or not. So it's very rapidly developing. What's also exciting is that as soon as you start developing new computational tools, they might have applications in other areas. So although we've been developing these things for physics, there's also applications of the same ideas in things as diverse as robotics or molecular genetics and drug design. And so there's really an exciting movement of development of targeted machine learning and AI tools for scientific applications that's having broad impacts even beyond physics. Okay, so let me just finish with a reminder of the story we've seen. So calculations directly from the standard model, from the equation of the standard model through this approach, this lattice field theory approach, are revealing proton structure and nuclear structure in new ways. So we saw some examples of basic details of the proton's internal dynamics that we're understanding for the very first time by combining theory and experiment, all the way to the very first calculations of simple nuclear reactions that have been done in the last few years, and really important theory input for searches for new physics beyond the standard model. And then as we continue to push the physics frontier, there's a new generation of provably exact physics-informed machine learning and artificial intelligence algorithms that has promise to open up calculations that were previously just too computationally expensive to do. And so it's already clear that with all of these exciting developments, the next decade or so will be a really exciting time as we continue this quest to understand the matter in the universe from the most fundamental particle building blocks. All right, thank you very much.
Great, thank you so much, Phiala. So, sorry, my voice is getting a little choky. But yeah, that was really
no worries.
Thanks. So we have a lot of questions already in the chat. Feel free to keep posting more questions as we go through these. But I don't know if we'll have time to go through everything. Maybe one basic one is, so what does Dr. Shanahan mean by when she talks about nuclear reactions? What quantities are actually being calculated? You give us a little bit of a taste of how the sausage is made, but what is it that is actually calculated, and what are the target observables for nuclear reactions?
Yeah. So if we're looking at a nuclear reaction, like say this one, you can break that down into several pieces. And some of those pieces are things that you can compute sort of by pen and paper. And then others of those pieces are pieces where you really need to do this full computational method piece. So one example of that would be this two-body contribution. And what that really means is, what's the difference between a photon interacting with the deuteron, that's this two-body nucleus here, and the photon interacting with a single proton or single neutron? And so you can really write that. You can say, let me measure a photon hitting a deuteron and compute that. It's called a matrix element. Compute that matrix element, that's a number. And then you can compute the same thing for the photon interacting with a proton or a neutron. And now that's one of the key pieces. That's not quite the same thing as the nuclear reaction rate, but you can use it to calculate with a bunch of other known things, the nuclear reaction rate.
Great. So let me see. So we have tons of questions about dark matter. Rightly so. They range on, there's questions about how can we say anything about modified Newtonian dynamics and modified gravity as perhaps explaining some of these phenomena. Then we have questions about what is the difference between hot dark matter and cold dark matter? Are WIMPs the most probable dark matter candidates? What are the possible? So let me read one last one. Is it possible that dark matter only takes action when the objects that are interacting are greater than a certain mass? So basically they just interact with heavy objects. What do you have? Do you have any thoughts on all these different questions?
Yeah, so look, it would be fascinating and very interesting if there was a solution to explain all the things we see that isn't the existence of some new particle or some new numbers of particles. So some sort of modification of gravity, that would be great if we can find out a modification that explains everything. So, this is sort of how science works. At the moment, there's no great modification of gravity that explains everything we see. Maybe someone will find one and dark matter will be a thing of the past, or maybe we'll find some dark matter particle. And I think we sort of have to be agnostic on that until we know more. And so the only thing we can do is we can keep looking for different signs of dark matter, both here on Earth and in the universe. We can keep trying to find better theories that explain everything that we see in other ways. And that's sort of all we can do. As for different things dark matter can be, I don't want to postulate on what it could be. I really have no sense. Someone asked whether these WIMPs, weakly interacting massive particles, are the most likely. No, I don't know how I would say what's the most likely. I think we have not enough constraints right now. We have a lot of theories, many of which explain some observations better than others. Others explain other observations better. It's sort of a big open question. I think it's one of the big mysteries of our age is, what is dark matter? Is there dark matter? A lot of these constraints assume that there's only one type of dark matter particle, because as soon as you say, well, what if there's 20? It gets much harder to constrain any sort of space. And so, but of course, maybe there's 20 different things which altogether make up the dark matter, and any one thing only makes up some fraction. All of these things are possible. So it's really a big unknown at the moment.
Yeah, to me, it seems more likely that there's a dark sector. But
it feels like it, since we know there's so many standard model particles, it feels like there should be a whole dark sector, but who knows?
Okay, so there's a couple questions about quantum computing, but before we go there, there's a question about measuring the pressure of the proton. So they're asking, how do you measure the pressure due to quarks individually inside of the proton? But maybe just more generally, can you explain how the pressure itself is measured of the proton at all?
Yeah, so this is a little complicated, but what you actually measure is the energy momentum tensor, right? You might have heard also of the stress energy tensor, same thing, inside the proton. And that can be written in terms of a quark piece and a gluon piece. But it's true that the separation between the quark and gluon pieces is sort of a scale dependent question. And so to really split them up, you have to specify an energy scale. And then if you go to a different energy scale, they'll mix up a little bit again. So this it's true that separation isn't crystal clear. What we actually compute are these, I mentioned this word before, but these matrix elements, the energy momentum tensor. What that means is you take the energy momentum tensor and you compute it inside a proton state. You say, in a proton state, what does this evaluate to? And you can write that down as a function of momentum. And then the Fourier transform of that, you can relate to this pressure distribution. So the intuition for that is if you think about a stress energy tensor or an energy momentum tensor, you get things like pressure on the diagonal and things like shear on the off diagonal. And that's sort of how that all fits together.
Great. So we have several questions about quantum computing, which you didn't touch on, but I think they're just triggered by the fact that, you're working on different novel ways of trying to study nuclear physics and particle physics. So the questions basically are on the range of, can quantum computing allow us to, will it have any influence in nuclear and particle physics, or will it allow us to have more efficient algorithms to access observables of the kind that you're interested in?
Yeah. So in many ways, quantum computing could be a very natural way of doing calculations of a quantum field theory. I mean, it even sounds like it should be natural. And in many ways, it could be a natural venue. Some quantities we would expect to be easier if we had a great quantum computer, and some we expect to be easier classically. So it really depends on exactly what the quantity is that you're interested in. The problem is that right now, quantum computers aren't good enough. That means don't have good enough coherence and enough qubits that can all stay coherent together for a long enough time to really compete with what we can do on these massive classical computers for almost anything in this particular area in particle and nuclear physics. However, there's lots of people working really hard on ways to formulate the questions we want to ask on quantum computers so that when quantum computers get better, we'll be able to fully exploit them for this. So my sense is that this horizon is quite a way away when we'll really be able to beat classical computers, which are still evolving. I'm not sure if it will be in my career time that's really, that we really reach that. Maybe it will, but it might be in your career times. So quantum computing is certainly very exciting, has a lot of potential. It's not there yet, so we have to wait and see.
Yeah, great. So I have a couple questions that I'm going to tie together. That are just more perhaps on the career advice side. So what are your thoughts on, what does it take to be a good physicist? So the person says, I'm a freshman in college studying physics. And what should be my next steps to contribute? And then another related question is, can you tell us about your journey towards being a theoretical physicist in nuclear and particle physics? Confused in both fields. So I think perhaps maybe they mean that they're confused in the distinctions of both fields, and how to go from their current master's program. So
okay.
Just to recap, what does it take to be a good physicist? What are the path, what are the lessons you've learned in your path? And how do you go from being, say, a college freshman to to where you are now?
Okay, there's a lot in there. So let me
Yeah,
answer
so
some pieces, and you can remind me if I miss bits.
good.
So to be a good physicist, I think one of the most overlooked pieces is creativity. It sometimes feels early on in your education that there's this great divide between the sort of more creative subjects, languages, music, art, and the sciences and maths. But really, when you get to the research point, one of the things I love about doing physics is that it all comes back together again. And that, sure, there's a lot of, you need to love maths and be good at maths. Computing helps a lot, all of these pieces. But the really good physicists also manage to do something really creative and not just computing the next thing on top of what was already known how to compute, but somehow pull together ideas from different areas and do something exciting and new. And that, it's a hard thing to learn. I think we all do it to different degrees. Some people are really amazing and do it, every day. Some people spend their entire careers doing much sort of more linear things and can be really great in another way of being, hyper focused and precise. There's sort of multiple ways of being good physicists, but I think the hardest one to learn is how to bring creativity in. And I think the only way to really learn that is to practice it, to even early on in your career, allow yourself, trust yourself to brainstorm and try to think about things in a different way from how you're being taught, and to not assume that just because you haven't heard it that way that you're automatically wrong, but to follow up on the thought and see where it goes, and to learn how to self-check, learn how to sanity check yourself and know when you're right and when you're wrong. Because that's the other really important thing for research, is there's no one to check with if you've done something really new. You sort of have to stake your career on knowing that you've done everything right and you believe yourself, even if no one else does. And getting the confidence to do that, that's something you can practice really early on. That you know that you've done your problem set all right, and you don't have to check with your friends or check with the answers, because you checked it in many ways. You developed methods of convincing yourself that you're right. So I think these are some skills that you can develop as you go that really help you down the line. So the skill of developing ways of having confidence in yourself, and the skill of thinking outside the box, being interested in lots of different things and trying to figure out how they connect, whether there's any intersections. Often that's the way advances are made, is by seeing different areas and realizing that maybe a tool applied to something different actually could be modified and make a big impact on this area where that tool had never been considered. And so being broadly interested and trying to build connections, which you can do all the way through your education. You can go to talks in different areas, you can read broadly and try to figure out how things connect. I think these are very useful things. How to figure out exactly what you want to do for research. Now my answer's maybe a bit funny. My answer's going to be, I think you don't need to worry about it too much. I think you should do something that's really exciting for the moment, and over your career, what you work on will evolve adiabatically as your interests evolve. And you certainly don't need to decide sometime in undergraduate or at the start of graduate school that you want to do particle physics and work on dark matter and do that for your whole life. I mean, if you know that, that's great, and you can build a career on that. But if you don't know, it's perfectly fine to do something that's exciting and let it evolve. I've certainly gone quite far from being a pen and paper theorist. Now I do massive supercomputer calculations. In the last few years, I've been developing new machine learning things. I never would have imagined that when I thought I would be a, hardcore pen and paper person forever when I was a student. It's just evolved, and you get excited about new things. So I think the stress about figuring out exactly what you want to do can really be eliminated. Just figure out something that you want to do for the next few years, and you can go from there. It doesn't need to be the perfect choice immediately. And so that, I guess, leads into my answer to, I think the last part of that question was some of the other things you can do as an undergraduate is get involved in research. And again, you don't have to pick exactly the right thing. You can just get a sense for some part of research and something about what research is like. And then it's fine to change between, explore a few different things, try some different research topics until you find something that suits you. It's also fine to start one, love it, and keep going there for a long time. There's really no one right way. I would say the right way is trying to get involved in something.
I mean, that was a great answer. I have a question for my own benefit. So, I mean, you touched on the idea that creativity is perhaps what makes really great physicists stand out, and I largely agree with this. I mean, I think it's, but how do you personally balance, your more creative juices from flowing from like the everyday pressures of producing something in science, right? I mean, there's this idea that faculty, they either have to publish or perish, right? So there is a pressure to produce results and have something, and I think everybody feels this, but there's some your creative juices sometimes can direct you towards going into directions that you're trying to tackle big and harder questions in a more creative way that perhaps may not have any answer, right? I mean, like folks that are doing dark matter searches, right? They have to be really comfortable with the idea that they're going to try to do something really ambitious and creative, but at the same time, they could find nothing, right? And so how do we kind of, how do you personally balance these two things, trying to be super creative, but also having this pressure to have some outcome?
Yeah, I think you use the word balance a number of times. I think that's really the right word, is that for me, I think it fluctuates year by year, but I hope on average, I have something like 80% of my efforts is spent on sort of more mainstream things, or things that have become mainstream, where there's a fairly clear path to where it's going. And the reason that number is so high is because of all of the junior people in my research group. I would never want to take on a student or a postdoc for a completely speculative, creative, awesome project that might totally fail and leave their career in a mess, right? And so for me, the pressure on is not so much publish or perish, because my position's secure, I guess. I did feel that more a few years ago. So for me, that pressure really comes from the junior people in my group, where I don't want them to suffer because I'm trying to be creative. So there's a large fraction of my work which certainly has elements of creativity. I think almost every project has to have a spark, but there's a good path forward. And then the other part are really things where I sit down and try to think of something, or I'm inspired by something and want to push it a bit further. And often that takes a lot longer to converge, because again, I don't want to get junior people involved until I think it's going to go somewhere. And so it'll be over some time, maybe even years, it will coalesce into something. And then sometimes that turns into an exciting research program, and sometimes it doesn't. Actually, a whole bunch of this work on machine learning and artificial intelligence started off like that, of several years of thinking about something until it coalesced into something solid enough for a first project. And now it's a very well-established research program that many junior people are working on, that's, I think, very secure. But the beginnings were very much one of those creative, out of the box, there's this problem and I want to think about a radical way of trying to address it. And honestly, more of those fail than turn into long-term research programs, or some might lead to one fun paper and then never go anywhere after that. But that's sort of the fun of it. Some people in the field are amazing at this. And I would say, I think the most amazing examples of people doing really important creative work are usually people who don't have students or postdocs. And probably that's because they can spend much more of their time on risky things without risking someone else's career. So it's a balance. I also get a lot from working with junior researchers, so I'm happy with this balance. But other people find another balance.
Yeah. All right. So 80-20 is a right recipe.
Yeah, I feel like it's that over time, although it goes, there might be a time when I try to set some months for starting something exciting and new, and then inverted, but then for a few years after that, it will be, following up on that.
Yeah, that reminds me. So I'm currently occupying Robert Edwards' office, which we both know quite a bit. And I think he told me that during like the winter break, he like stops doing normal research and then plays around with a new idea. So
yeah.
So maybe I should.
I think sabbaticals are great for this too. Sabbaticals are really fantastic.
Yeah.
6 months or a year every 7, and that's about the right ratio. Even if you just spent the entire sabbatical doing creative stuff and all the rest of the time doing other stuff.
That's great. Well, Phiala, I mean, I could talk to you forever. We still have many more questions on the chat, but let me close with a couple of fan mails here from folks on the chat saying, this was a really great lecture. Thanks a lot for the great comprehensive presentation. Other ones are answering as we speak. And I think this is in reference to maybe a talk that you gave, but I'm not sure. I'm a fourth, and this is what it says. I'm a fourth year theoretical physicist in the University of Edinburgh, and I attended the Higgs talk in March 2020 or March 22, 2023. Is that something that you gave?
Yeah, we might have met.
Okay, so saying thank you for an interesting talk, and that on the 22nd of March as well. So Phiala, appreciate it very much. I think everybody really enjoyed this talk. So thanks for taking time out of your busy schedule to join us. Always a pleasure. And hopefully I'll see you, I guess I'll see you at Lattice, hopefully.
Yeah, see you in a month or 2.
All right, see you in a month. All right, take care.
See you later. Have a good one.
Yeah. All right, Tom. I think we're good. We can stop streaming. Thanks, everybody. So for those of you that have asked questions about the streaming and the recordings of the sessions, I send an email. Also send an email to you about information regarding the Python for STEM. I promise in that email that I will be sending updates about the mentoring program shortly. Okay, so hope everybody's doing well. And I look forward to seeing you guys tomorrow. All right, take care. Oh, one last thing. So people are asking, what is the best way for you to take, what is my advice for how to make the most out of these lectures? You don't have to record this. But what I was going to say is that you can, what you should be doing is just basically getting a taste of different, careers and hearing what different scientists have to say, and learning about a variety of different topics. If you don't understand everything, that's okay. The first time that you hear a new advanced topic, just you need to absorb it a little bit. The second time you're going to get, it's going to absorb even further. Eventually you hear these topics so many times that, you start memorizing these ideas, and then hopefully with time, you will learn, what these different concepts really mean. And so all I hope that you get is just a little bit of knowledge, a little bit of understanding, and hopefully a little bit of inspiration to want to pursue careers on these paths. If you choose not to, but at least you have a little bit of appreciation on different careers. That's all I would hope for. Okay, so that's what I'm hoping that you would get out of this. So with that, now I really will go. Take care, everybody. Bye.